Chemistry 1401. This is practice exam 2. And the first part, we get started by looking at question number 1, which asks us, which of the following is not a property of covalent compounds? Covalent compounds are made from nonmetals, and they're made by the sharing of electrons between nonmetals. The first says they have variable and typically low melting points. This is true. They exist as individual molecules. This is also true. They do not form ions in solution. Also true. The next one, they form extended crystal lattices of alternating ions. This is not a property of covalent compounds. This is a property of ionic compounds. And then finally, they're poor conductors of electricity when they are in an aqueous solution, and that is true. They are non-electrolytes because they don't form ions in solution. Question number 2 says, predict the charge of a nitride ion. Nitrogen is in group 5A, and nitrogen has 5 valence electrons, and so it has to gain 3 electrons in order to become isoelectronic with the nearest noble gas, which is neon. And so when nitrogen, when it gains those 3 electrons, it becomes N3 minus, and so the charge on a nitride is 3 minus. Question number 3, which of the following is the correct ground state electron configuration of an aluminum ion? Well, aluminum is in group 3A, and so it tends to lose 3 electrons in order to become isoelectronic with neon, so that would give us a charge of Al3+. Again, it becomes isoelectronic with neon, which has 10 electrons. And so if we write out the electron configuration for aluminum 3+, remember it needs to have 10 electrons. We're going to start with 1s2, 2s2, and then 2p6. If you tally up 2 plus 2 plus 6, we end up with a total of 10 electrons, and that is isoelectronic with neon. And so the answer is 1s2, 2s2, 2p6. Question 4. What is the name of Cu3PO42? Well, copper can have 2 possible oxidation states because copper is a transition metal. Copper can be either copper +1 or it can be copper with a 2+ charge. But phosphate, that doesn't change, right? A phosphate is a polyatomic ion that always has a charge of 3 minus. Now, if I have 2 phosphates, that means that I'm going to be taking that -3 charge and multiplying it by 2 times. So overall, I'm going to have a charge of -6. If I have 3 coppers and overall their charge has to be +6 to balance out my -6, what times 3 gives you +6? And the answer is +2 times 3 gives you +6. And so this has to be copper 2+. Now, when we have a transition metal and we want to identify its oxidation state, we have to use the stock naming system where we use Roman numerals. And so we can cancel out all of these answers here which don't even use Roman numerals. And since this is copper 2+, the name of this compound is going to be copper 2 phosphate. Question 5 is in the same vein as the last problem. It's asking us for the name of VSO42. Well, SO4, hopefully by now you know that SO4 has a 2- charge and it's called a sulfate. If I have 2 of those, if I take -2 and I multiply it by 2, I get -4. So that means that my vanadium has to have a +4 charge. Now, vanadium is a transition metal. It's element number 23. It's found in the 4th period of the periodic table. And so we have to use Roman numerals, the stock naming system, so we can eliminate these answers right here. But if the vanadium has a +4 charge, this will be vanadium 4 sulfate. Next question asks us predict the outer electron configuration of thallium with a +1 charge. Well, thallium itself has 81 electrons. It's element 81. If it loses an electron to have a +1 charge, then it's going to have 80 electrons. So thallium plus has 80 electrons. Now, outer electrons are anything after the noble gas that precedes it. So the noble gas that precedes thallium is xenon. And so after xenon, we have 6s2. Then we go into the f orbitals. We have 4f and we have 14 of those, so 4f14. And then we go into the d orbitals. We go up to the number 5, so we have 5d10. Now, if it was thallium, we'd have 6p1, but we've lost that electron. And so our answer is xenon, 6s2, 4f14, and 5d10. Next question asks us, how many d electrons are there in zinc with the 2+ charge? Well, zinc is element number 30. If we write out the electron configuration of zinc, the noble gas that precedes zinc is argon. And so after argon, we would have 4s2, and then we would have 3d10. That would be for zinc. But when we lose 2 electrons, we're going to lose them from the highest principal quantum number. Okay, so we're going to lose the 4s2 electrons, and we're going to lose the electrons from the orbital that has the highest principal. But when we lose 2 electrons, we're going to lose them from the orbital that has the highest principal quantum number, so we're going to lose the electrons from the 4s orbital. And so zinc 2+ is going to be argon and then 3d10, and so it will have a total of 10 d electrons. The next question asks us, which of the following ions will have the largest size? Well, by now you probably know the trend for atomic size is that it increases going from right to left across the periodic table, and it increases going down. So atomic size increases. And you should also know that the more positive a cation is, the smaller it will be, because the greater the effective nuclear charge will be on the remaining electrons. It's going to pull them in even tighter and tighter. And so the largest of these 5 cations should be either rubidium with a +1 charge or potassium with a +1 charge, because the rest of them either have +3 or +2 charges. And if we look at cations within the same family or the same group, and potassium and rubidium are in the same group, rubidium is farther down in the group than potassium. And so the largest one should be the rubidium cation. Next question asks us, which of the following correctly depicts the Lewis formula for a fluoride ion? By now you should know that a fluoride is fluorine with a -1 charge. Well, fluorine itself is in group 7a, so that means it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. But if fluorine has a -1 charge, it's going to take on another electron. And so this would be the Lewis structure right here for our fluoride ion. Fluorine surrounded by 8 valence electrons. Which of the following correctly depicts the Lewis formula for a neutral nitrogen atom? Nitrogen is in group 5a, and so it has 5 valence electrons. You write the atomic symbol. We start placing 1, 2, 3, 4 electrons around, 1 on each side, and then we're going to have to pair up another electron for the 5th electron, and we could put it on the top, we could put it on the sides, we could put it on the bottom, and so this would be the acceptable Lewis formula for a nitrogen atom. Question 11, what is the formal charge on the carbon atom in the Lewis formula for the methane molecule? Well, carbon has 4 valence electrons, and hydrogen has 1 valence electron, and there's 4 hydrogens. That means we have a total of 8 valence electrons in methane. Now, one of the rules of drawing Lewis structures is that hydrogen can only ever form 1 bond, and so the carbon must be the central atom, and it must be surrounded by the 4 atoms. Since there are 2 electrons in each one of these bonds, we have 2 times 4 bonds, so that covers all of our 8 electrons. Now, formal charge is calculated like so. We take the number of valence electrons, then we subtract the number of bonds, and then we subtract the number of non-bonding electrons. And so for the carbon has 4 valence electrons. We subtract the 4 bonds, and we have no non-bonding electrons. 4 minus 4 minus 0 gives you 0, and so the formal charge on the carbon is 0. Question 12 asks us, which of the following molecules will possess a double bond? We'll start with xenon tetrafluoride. Xenon has 8 valence electrons. Fluorine has 7, and there's 4 of those, so that's 28 plus 8, which gives us 36 valence electrons. We'll put our xenon in the center like this. We'll put a fluorine over here, another fluorine here. another fluorine like this, and another fluorine over here. And we'll fill up all of their octets. Remember, fluorine always has one bond and 3 lone pairs. So far, I've used up 8 times 4, which is a total of 32 electrons. So that means I'm going to have a lone pair here and a lone pair here. There's my Lewis structure. For xenon tetrafluoride, there is no double bond. Next, we'll look at HCN. Hydrogen has 1 valence electron plus the 4 from carbon plus the 5 from nitrogen. That gives us a total of 10 valence electrons. The carbon will be in the center. Hydrogen can only have 1 bond. Carbon must have 4 bonds, so we put 1, 2, 3 like this. Nitrogen always has 3 bonds in a lone pair. There's our Lewis structure for HCN. There is no double bond in HCN. Next, we have HCCH, so that's 2 valence electrons, 1 for each hydrogen, plus 8 valence electrons, 4 for each carbon. So that gives us a total of 8 plus 2, which is 10 valence electrons. We have our carbons attached like this. Hydrogen can only have 1 bond, but carbon has to have 4 bonds. And since it only has 2, we're going to put a triple bond in between the 2 carbon atoms like that. We've used up all 10 electrons, and there is no double bond in this molecule. Next, we have this formula here, HCOOH. We'll put our hydrogen attached to the carbon. Carbon always has 4 bonds. 1, 2, 3, 4. I'm just thinking out loud here, so I'm going to have an oxygen. Oxygen can only ever have 2 bonds and a lone pair. So I'm going to have an oxygen like this. One of the oxygens is going to have a single bond to hydrogen, but the other one is going to have a double bond, like this. And therefore, we've used up all the valence electrons, right? We have 2 from the hydrogens. We have a total of 12 from the 2 oxygens, so that's 14. And we have 18 when we add the 4 from the carbon. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we've used up all of our valence electrons, and we can see that this molecule does have a double bond in it. Lastly, if we look at sulfur tetrafluoride, sulfur has 6 valence electrons, fluorine has 7, and there's 4 fluorines, so that's 28 plus 6, which gives us 34 valence electrons. We'll put our sulfur in the middle like this. We put a fluorine on each end, and we put a fluorine here and a fluorine here, like this, okay, like that. Now we've used up, let's see, I have 8 for each fluorine. 8 times 4 is 32, 33, 34. And so this has the seesaw shape, and it does not possess a double bond. The next question, which of the following species is an electron deficient compound? We learned 2 exceptions where we have electron deficient atoms, and those are boron and beryllium. Aluminum could also be in there as well, but you see that the only one of these that contains either of those atoms is beryllium hydride. In fact, the Lewis structure of beryllium hydride, beryllium has 2 valence electrons, and then we get 1 for each hydrogen. There's 2 of those, so that means a total of 4. That means that beryllium could only form 2 bonds like this and adopts a linear molecular geometry. And so beryllium hydride is our electron deficient compound because beryllium does not have an octet. The next question, what is meant by resonance stabilization, is just a qualitative question to make sure you understand what resonance stabilization means. First one, a molecule without resonance is more stable than any molecule with resonance. Well, we know that that's not true because resonance helps to stabilize a molecule. The next one, the energy of a real molecule is represented by a superposition of Lewis formulas or several Lewis formulas is more stable than any one of those individual Lewis formulas. Well, that's what resonance stabilization is. We can't give one adequate Lewis structure that describes the molecule or ion completely. And so we have several Lewis formulas or Lewis structures that help us to rationalize why the molecule is more stable. It shows the delocalization of electrons, and therefore we show the increase in stabilization. The next one, the energy of the real molecule is represented by a superposition of Lewis formulas is less stable. Well, that's not true. The energy of a real molecule is represented by Lewis formulas is lower in energy than any superposition of its Lewis formula is also untrue. And a molecule with resonance is more stable than any molecule without resonance. Well, that's not necessarily true. Next question. Which choice below ranks the elements chlorine, cesium, manganese, germanium, and calcium in order of increasing electronegativity? On our periodic table, we know that when we go up a group and when we go from left to right across a period, we have increasing, I'll just write big E, big N for increasing electronegativity. And so if you look at, what they're calling the most electronegative elements in all of these possible answers, you can see that calcium, cesium, and manganese are way far away from chlorine, right? Chlorine is in group 7A, so it's definitely the most electronegative of any of the elements in the list. And then we just look at the rest of the order. Cesium is actually the least electronegative element there is. And so this is going to have to be our answer. Again, if you compare cesium and calcium, calcium is in group 2A and cesium is in group 1A. And it's also lower it's in a higher period. And so it's definitely going to be less electronegative. And so here's our answer, highlighted in yellow.